In today's lesson, we are going to be tackling a very elegant problem in 3D geometry. How far is a point from a line or a plane? Now, that might sound simple, but in three-dimensional space, this question is like asking, how far is a drone from a flight path? How far is a point in space from the floor of a building? How far is a satellite from a communication beam? These aren't just theoretical, they're practical. And today we'll use vectors to find exact distances in situations where a ruler just won't cut it. And here's what's really exciting. We're going to combine direction vectors, dot product, and projections. We'll use clean, elegant formulas based on the geometry you've already mastered. And most importantly, we'll learn to describe what shortest distance truly means in 3D space. So whether we're finding the perpendicular from a point to a line or dropping a vertical to a plane, you'll walk out of this lesson hopefully with a new power, the ability to measure the invisible and describe space with precision. So let's go ahead and get started. So let's start by thinking in 2D. And just looking at the distance from a point to a line. So we're used to seeing a line in standard form, ax plus by plus c equals 0. That describes our line. But if we want to think about what the shortest distance would be, we have to think about it in terms of what's happening if we have 2 points. So the shortest distance from this point here, P, which is x1, y1, to this line that we have here is going to be that distance px. It's going to be this line right here. Well, that's perpendicular to the line. And remember, we've been describing that as the normal. The normal is perpendicular, and it's that line px is measured along the normal through point P. That distance is shorter from P than to any other point on the line. So we know that the distance that we're looking for is the magnitude of px. So the magnitude of this distance from here to here, or from here to here. And that distance, like I say, is just the magnitude of the line px. Well, if we think about what we really have going on here and layer on what we know about projections, we know that we can get the magnitude of px. We can get that by taking the projection of the other line QP. We take the projection of this line QP onto the normal of n. So how much is this projecting onto there? So remember from lesson 7.3, the formula for the magnitude of the projection, in this case of QP onto the normal, will look like this. It's going to look like this one right here. So that distance, we can say that distance then, the projection is equal to the distance, is equal to the magnitude of QP dot with n all over the magnitude of the normal vector. So we can develop a formula for the distance from a point, some point P, x1, y1, to a line with a scalar equation of ax plus by plus c equals 0 if we take the projection. So let's let Q, with the values of x, y, be a second point on the line. And let's see if we can figure out. Now, I've already kind of given it away because you can see the equation that we're aiming for on the bottom here. But I'm going to show you how we actually get there. So we know that we can take the projection of QP onto the normal n, and that's going to be equal to the magnitude of PQ dot, PQ dot n all over the magnitude of n. So if we want to know PQ, well, we know that PQ or QP, we just could reverse it, it doesn't really matter, is just going to be x minus x1 and y minus y1. We're just in 2 dimensions. The normal for this, remember the normal when we have the scalar equation, not the c value, is just our a and b value. So the normal for this is ab. We've already got a lot of information. So if we put this all together and we do QP cross n, well, we end up with I'm just going to do that part over here. We have x minus x1 and y minus y1 dot product or dotted with AB. That's going to give us a x minus x1 plus, because we're dot product, b y minus y1. Okay, so now if I'm starting to fill this into what's happening here, we can see that I have the magnitude of a x minus x1 plus b y minus y1 all over the square root of a squared plus b squared. Now, we need to simplify this a little bit in order to make it look like what we're aiming for. So since q is since the point qxy is on the line ax by plus c equals 0, then we can kind of think of this as being ax plus by equals negative c. We can think of it that way. And if I go ahead and I say, well, I have ax, so this is ax is x minus x1 plus b y minus y1. Well, if that's equal to negative c, we kind of already know what's going on here. So we can expand this out, and we're going to say ax minus ax1 plus by minus by1. I'm going to rearrange this because it's addition and subtraction. There's no reason we can't rewrite it any way we want. So I'm going to put ax plus by is minus ax1 plus by1. And we know that this is equal to negative c. So I can have ax plus by minus negative c gives me plus c. So this kind of gives us a little clue as to where the top part of that equation came from. When we put it all back together, we get the magnitude of ax plus by plus c all over the magnitude of our normal vector a squared plus b squared, take the square root. Okay, so let's try it both ways with a question and see if we happen to get the same answer. So remember I said that the original projection is QP dot n, the magnitude of that, all over the magnitude of n. And then we just derived this formula that really should be equal. We have the magnitude of ax plus by plus c all over the root of a squared plus b squared. So let's start with this one over here. I'm pointing at it. You can't see what I'm pointing at. Let's start with this one. So this method requires a point on the line. We already know another point Q, but we need to know an actual point on this line. And we can find the x-intercept just by subbing y equals 0 into the equation of the line. And I'm just going to do that quickly here. So I'm going to solve for x, where y is equal to 0. Plus 4 equals 0, so 2x equals negative 4, and x is equal to negative 2, so I know I have a point at negative 2, 0. Okay, so I have my normal. Remember, I can get the normal just from my coefficients in front of my x and y. So my normal is 2, negative 3. Now I need to figure out this QP. Well, I have a point Q, now I have a point P. So if my point Q is 3, 5, and my point P that's on the line is 2, 0, then I can get QP by taking P minus Q. So I get negative 2 minus 3 and 0 minus 5. So this is equal to negative 5, negative 5. Now I have everything I need to do the dot product. So we can say that the distance is equal to the magnitude of QP dot n all over the magnitude of our normal vector n. So this is negative 5, the magnitude of negative 5, dotted with 2, negative 3, all over the magnitude of the normal. And I'm just going to go ahead and fill that in. So our normal was 2, -3. So it's 2 squared plus -3 squared. Remember, dot product is just taking this times this plus this times this. So we're going to have -5 times 2 plus -5 times -3 all over root 13. That's what that equals when we work it all out. So if I do all of this, I end up with -5 times 2 is -10, and we have plus 15 there, all over root 13. And that gives me a magnitude or absolute value of 5 all over root 13. So we have 5 over root 13. No need to rationalize because we really just want to get a value, and 5 divided by root 13 is 1.39. Now that's not an exact value, but that's really how we're going to compare. Okay, so now let's try it the other way. So now I have my equation of the line. I'm going to sub in my x, y values into that equation and use still my normal or my a squared plus b squared on the bottom. So d equals, we have a is 2x. It's the x value of our point Q, or the point that we want to know the distance from, plus, it's minus 3 times 5 plus 4, all over that same root 13, because it's the same as over here. But we'll write it out anyway. Okay, so my a value is 2. So that's 2 squared plus my b value squared, which is -3 squared. So now we get 2 times 3 is 6, minus 15 plus 4 all over the root of 2 squared plus -3 squared, which is indeed root 13. So 6 minus 15 plus 4 gives me -5. But remember, that doesn't matter if it's negative because I'm taking the absolute value of it. So I end up with 5 over root 13. I did actually end up with exactly the same. And so if it's exactly the same, it's going to give me the exact same numeric value. So there's a couple of different ways we can do this, and it just depends on what information we're given. So if I have a point and the scalar equation or the standard equation of a line, then I can go ahead and I can use this. Now, I also could do the QP dot n over the magnitude of n. I just have to do a little bit more first. The dot product one gets a little bit easier if I have both of the vector equations of the line. So we've just learned that the distance from a point to a line in 2D can be represented by this very handy equation right here. So we have the magnitude of ax plus by plus c. So long as we know a point and we've got that form of the equation, that scalar form of the equation, we're off to the races, all divided by really what ends up being the magnitude of the normal vector taken directly from our scalar equation. So a squared plus b squared, take the square root of it. So if that's our distance from a point to a line equation in 2D, what do you think the distance from a point to a line in 3D is going to look like? Well, the distance from a point to a plane in 3 dimensions is calculated pretty much the same as the distance from a point to a line in 2D. It's measured along the normal to the plane. So let's say I have my plane and I'm drawing it as a parallelogram. Remember I said that I think last lesson that if we're drawing a plane, it's easiest to draw it like a parallelogram. So if we have a point Q, let's put Q up here. We have point Q that is not in the plane. And we have a point P naught that is on the plane. And that's any point on the plane. Then the distance qn, or q to the normal, we'll call that the normal, from q to the plane is the projection of p naught q onto the normal. So this is going to be the projection of this onto here. Oops, onto here. I don't know why it's erasing. This onto there. Okay, so if that's the case and it's working exactly the same as 2D, then our equation here for distance is not all that different. I have ax plus by plus cz, there's my third dimension, plus that value d, all over that magnitude of the normal. And now the normal has three components, an x, so a squared, plus a y, b squared, plus the z, c squared. So the numerator here uses the equation of the plane with the coordinates of the point substituted for x, y, and z, exactly the same as we did in 2D. And the denominator is just the magnitude of the normal. So let's try a question. I wish I had have left myself a little bit more space here, but I think we can do it. So here is our point, and it has our x, y, z coordinates. Here's our equation. So let's go ahead and let's just plug it in. So we have the magnitude of ax plus by plus cz plus d. So we have 9 times 1, 9 times my point, my x coordinate, plus y, well, that's just 2. I'm going to make that look more like a 2, plus z, and z is 3, plus our d value 7 there on the end, all over the square root of our direction, 1 and 1. So we have the square root of 9 squared plus 1 squared plus 1 squared. That gives us 9 times 1 is 9, plus 2 plus 3 plus 7, all over the root of 83. That's going to give us an absolute value of 21 over root 83, which is 21 over root 83. Now remember, I said we really just want values for this because I want to know the actual distance. So I don't even need to rationalize because I'm not keeping it as an exact value. So we can put it in terms of a decimal as 2.31 units. That we could say 2.31 units. Now, what if I want to have the distance between two parallel lines? We can pick a point on one plane. We want to know the distance between two parallel planes. Well, we can just pick a point on one plane and use the distance from a point to a plane equation using the second plane. So let's look at an example of this. So let's say I have plane number 1. Here we go. Plane 1 is 2x minus y minus 2z plus 3 equals 0. My second plane is represented by 4x minus 2y minus 4z plus minus 9 equals 0. Okay, so we know that they're parallel, and since we know that they're parallel, we can prove that they're parallel, but we know that they are because it told us in the question. But if we wanted to think about this, our n2 value for -2, -4, of 4, -2, -4 is actually a scalar multiple of our n1 value of 2, -1, -2. So that proves that they're parallel, but we already knew because it said it in the question. So what do we want to do? Well, we are going to find the distance, we are just going to pick a point on the plane. The simplest one to use is the intercept. And I'm going to say, let's take the intercept from this first equation. And the reason that I'm saying that, and we're going to find the y-intercept, is just because we just have a y there. There's no other numbers. It's pretty easy to do it. So if I have 2 times 0 minus y minus 2 times 0 plus 3 equals 0, that gives me -y equals -3 or y equals 3. So I know that I have an intercept or a y-intercept at 0, 3, 0. Now I'm just going to go ahead and use that into the second plane. So I used the first plane to get my intercept. Now I'm going to use the equation for the second plane in my distance equation. So my distance is going to be equal to, we're going to say the second one, so 4 times 0, that's the point on the line, 2 times 3, the y value, minus 4 times 0 plus 9. Oh, do I have it wrong? No, I don't. Minus 9. I keep losing that minus 9. I don't know what's happening there. All over the root of our normal. So we have, you can use either one. It doesn't matter. We'll use the one for this one. 4 squared plus negative 2 squared plus negative 4 squared. So that gives us negative 15, the absolute value of negative 15 all over root 36, which is 15 over root 36, which is 15 over 6, or 3 over 2. And we could divide that out if we wanted to, but I just wanted to use it as a little bit of an example of how we could do that for two parallel planes, but just only using the equation that we know from a point to a plane. So there's a couple more things that I want us to think about. So what if I'm in 3D and I don't have a normal? Well, I have a line, I still have my 2 points. I know I will have a perpendicular line here. Well, if I really want to know what's going on here, I can take, if I know this point and I know this point, I can get this line segment here by getting the projection of PQ onto D. Well, the projection of PQ onto D, remember, is just the dot product. So it's PQ dot D all over the magnitude of D. Once I know QX, and I already know, I'm assuming I know my points x1, y1, and we'll say x2, y2. So long as I know that, and I've been able to figure this out, well, this is now just a right-angled triangle problem, and I can go ahead and just use my Pythagorean theorem, where I can take the magnitude of PQ squared, which is my hypotenuse here, minus the magnitude of this line segment QX that we just found squared, and that's going to equal my normal squared. So I am able to go ahead and it's the magnitude of it, the magnitude of the normal squared, and that's going to help us out when we go when we're trying to tackle these problems. Now, the other way that we can think about this, remember, if we draw it out, we actually have two parts of a parallelogram. Well, I can use the cross product to figure out the area of a parallelogram. And if I think about the area of the parallelogram as being PQ crossed with D, and the formula for area of a parallelogram is the base, which is this distance here, times the height, which happens to be the normal. So if I want to figure out what the normal is, I can use what I know about parallelograms, rearrange this equation to get h by itself, and this will tell me that h is equal to the cross product of PQ, so PQ cross D, all over that base or the magnitude of D. So let's try this one out and let's see if this actually does work. So remember, we've got a line, some line like this D, and we have some arbitrary point P. We also have a point on the line Q. We're able to connect those. We have some distance X that happens to be perpendicular. Okay, and so now we have a point. Here is our point P. We have our line. Here is our point that's on the line. Here is our direction. So let's try it both ways. So I know that I can get this distance here, right here. I'm going to do that in a different color. I can get this distance right here by taking the projection that PQ makes onto this line here, this D line. And to do that, I can take the dot product. So there's a couple of things I need to figure out here first. So I need to know PQ, and that is simply Q minus P. So -1 minus 3. We have 5 minus 1, and we have 2 minus 4. So that gives me a value for PQ, or coordinates for PQ, of -4, 4, and -2. Now, I also know my direction vector. I have one because it's given to me with the line. So I have my direction vector of 1, 2, 3. So now I can go ahead and I can plug this into my equation to get the magnitude of this line segment right here. I can't stress that enough. We're not getting the answer yet. We're using this as a means to an end. So I am going to take the magnitude of PQ dot D all over the magnitude of D, and that's going to give me -4, 1 times 1 plus 4 times 2 plus -2 times 3. Make sure I've got all my brackets there, all over the root of my direction, the magnitude of my direction vector, which is the sum of the squares square rooted. So 1 squared plus 2 squared plus 3 squared. So that gives me a value of -4 plus 8 minus 6 all over root 14. So this tells me that the magnitude of my line segment, or the length of that line segment QX, is 0.5345. And I'm going to hold on to a few decimal places. So that's telling me that that right there is 0.5345. So QX is equal to 0.5345. Well, I know PQ. I can get the magnitude of PQ. So if I want to know the magnitude of PQ, I'm going to do the same thing. And so PQ was -4 squared plus 4 squared plus -2 squared. So PQ is root 36, which is equal to 6. This is telling me that I have a magnitude of 6 along here. So now I'm just going to use good old grade 9 Pythagorean theorem that can tell me that this normal, the direction kind of, but we're going to say the normal squared is equal to 6 squared minus 0.5345 squared. And that's going to give us a value of 5.97. That's the distance. You know what? I am going to change that back to the distance. That's the distance of that line segment. So that's how far away the point is from the line. Because it's the shortest distance between 2 points is dropping the perpendicular. And that's really what we've done there. I don't think I mentioned that before. Okay, let's try it the other way. Let's try it by thinking of it as a parallelogram and finding that height instead. Well, we still need PQ. We've already figured it out. It hasn't changed since the last time, since the other side of the page here. So -4, 4, -2 is our value for PQ. Now this time I'm crossing PQ with D. So PQ crossed with D, and that's going to be, our PQ is -4, 4, -2. Crossed with our D, which is 1, 2, 3. Remember, I'm going to start in the middle. 4, -2, -4, 4. Crossed with 2, 3, 1, 2. So this is going to give me 4 times 3 is 12. Minus -4, so plus 4. -2 times 1 is -2. minus negative 12 becomes plus 12. And negative 4 times 2 is negative 8 minus 4. So that gives me 16, 10, negative 12. And now I know that I have to go ahead and just do it over the magnitude of our direction vector. So 1 squared plus 2 squared plus 3 squared. Now, don't forget, we also have to take the magnitude of this. That's really what this is saying, is that we need to take the magnitude of it. Don't draw it like that. That's not right. Okay. So we're going to take the magnitude of it. Same processes down here. 16 squared plus 10 squared plus negative 12 squared all over our root of 1 squared plus 2 squared plus 3 squared, which we already know is 14 because we did it over here. So that gives us the root of 500 over the root of 14. And guess what? That also equals 5.97. So depending on what information you're given or how much work you actually want to do will depend on which one of those ways that you do, which one of those equations that you decide to use. Okay, last thing we're going to talk about for today is what if I have the distance between skew lines, if I want to find that out. So remember, these are lines that live in 3 space but don't touch and don't run parallel to each other. So they're kind of like 2 train tracks on different levels going in different directions, and they're never intersecting. So the question really is here, what's the shortest distance between them? Well, the shortest distance is found along the line that is perpendicular to both skew lines. So we can create a vector from a point on line 1, P. So we're going to say we have a point on line 1, that's P, and a point on line 2, that's Q. And we want to think about this. So we have our 2 lines, and we haven't written them like this for a while, but I have line number 1 is equal to point P. Remember, that's our point vector on the line, times S times some scalar multiple times our direction vector for line 1. And down here we have line 2, which is equal to point Q. It has point Q on that line, plus T, our scalar multiple, times our direction vector 2. So P and Q are just points on the line. D1 and D2 are our direction vectors. So if we take the cross product of the direction vectors, we get a vector that's perpendicular to both lines, which means it points in the direction of the shortest distance between them. That is our definition of a normal. So to get our normal, we take the cross product between our 2 direction vectors, one from each line. Once we've done that, we can find the component. We can find the component of PQ that projects onto it. So our formula ends up being that distance between 2 skewed lines is the magnitude of PQ dotted with N all over the magnitude of the normal. And this gives us the length of the projection, which is the shortest distance between 2 skew lines. So let's do an example. Okay, so we have 2 lines here. So we'll call this, let's call this line 1. Doesn't really matter. Here is our point P, and this is our direction vector 1. This will be line 2. Here's my point Q on that line, and here's my direction vector 2. So if I have D1 is equal to 2, 3, 4, and D2 is equal to negative 1, 1, 2, then I can take the cross product of that to get the normal. So the normal will be D1 crossed with D2. So D1 crossed with D2, we have 1, 2, negative 1, 1, 3, 4, 2, 3. I'm going to cross them. So I end up with 1 times 4. I just realized I wrote them out backwards. That was what the big awkward pause was. Okay, so let's write them out the right way. I have D1 crossed with D2, which means I have 3, 3, 4, 2, 3, 1, 2, negative 1, 1. There, that's going to be a little better. All right. So this is going to equal 3 times 2 is 6, minus 4 times 1 is 4. 4 times negative 1 is negative 4. And that's going to be minus 2 times 2, which is 4. And then I have 2 times 1 is 2, minus 3 times negative 1, which is negative 3. So I have 2 minus negative 3 becomes plus 3. So that gives us 2, 0, 5 for our normal vector. So our normal vector is, the direction of our normal vector is 2, negative 8. Oh my gosh. Okay. 2, negative 8, 5, because negative 4 minus 4 is actually negative 8. Okay. So now let's find PQ. And PQ will be Q minus P. So 2 minus 1, negative 1 minus 1, and 5 minus 1. So PQ ends up being 1, negative 2, 4. Now I'm going to plug it all into my equation. So my distance is equal to the magnitude of PQ dot N all over the magnitude of N. So PQ dot N is going to be 1 times 2 plus negative 8 times negative 2 plus 5 times 4 all over the root of 2 squared plus negative 8 squared plus 5 squared. So that equals 2 plus 16 plus 20 all over root 93. Oh, I've run out of room. Okay, so let's just carry that on over here. And so 12 plus 16 plus 20 is 2 plus 16 plus 20 is 38 all over root 93. That's equal to 38 over root 93. That is approximately equal to 3.94 units of length. Okay. I feel like that was quite a bit tonight. I do want you to go ahead, or today, I'm recording this at night. That's why I said at night. So I want you to go ahead and do some of these practice questions, paying particular attention to 18, page 480, number 18. You may need to go back and look at what we already know to answer that question. As always, if you do have any questions, feel free to send me an email.